Hey everyone, welcome back to AP Calculus. This is Unit 5. It's all about applications of the derivative as it pertains to functions. Today we're looking at, in Lesson 4, concavity and points of inflection. So, first of all, what is concavity? So, the mathematical definition says that if f prime is increasing, then you are what we call concave upward or concave up. If f prime is decreasing, you are concave down on that interval. So concavity is more of a general word for kind of acceleration, if you think about that. So it's the rate of change of the rate of change. So if the rate of change of f is increasing, we're saying concave up. Likewise, concave down if it's decreasing. I oftentimes think of concavity, and I'll say the words instead of concave, I might say cuppy uppy or cuppy downy, because that's exactly what it looks like. It looks like a cup. So when you are concave down, you appear to be cupped downward. And when you are concave, well, I guess I put that in the wrong spot. This would be concave down there, and then concave up is up here. Notice that concave up doesn't mean increasing or decreasing function. It just means that the graph is shaped like a cup that could hold a liquid, right? So I can be increasing in concave up, or I can be increasing in concave down. I'll look at one side of it. So here's a function that is increasing in concave up. Notice it's increasing at a faster rate. Here's a function that's increasing in concave down. One of these looks like it could hold some water if you put a little edge, right, like a little block right here. The other one does not. It would just fall off, right? So increasing concave up, increasing concave down. So since we know that the derivative of a function indicates increasing or decreasing behavior, it should make sense that if we're trying to determine the concavity, and remember concave up means that f prime is increasing, then we need to find the second derivative of f. We need to find the derivative of f prime, which is f double prime. Make sense? Remember, the derivative of a function can be used to tell you if that function is increasing or decreasing. Since concavity is indicated by whether f prime is increasing or decreasing, we simply need to take the derivative of f prime. So here's the concavity of functions theorem. If f double prime of x is greater than 0 for all x in an interval from a to b, then f is concave up. Likewise, if f double prime is less than 0 for all x in the interval, f is concave down on that interval. We don't usually cite this theorem by name, and it's not necessarily have an agreed upon name. We just simply justify on a test by saying, this function is concave up on the interval from a to b because f double prime of x is greater than 0 on that interval. All right, let's take a look at one. So consider the graph of f shown below. Indicates the signs of f prime, f double prime on the interval from 0 to 3. Because f prime is decreasing, because f is decreasing, we know that f prime of x must be less than 0 on the interval from 0 to 3. Because f is decreasing, f prime is negative. But if you look at the slopes of these tangent lines, are the slopes increasing or decreasing? Well, the slope here is quite negative, but then it gets a little bit less negative, and then a little bit less negative. So as we go on, we're getting less and less negative, which means we're actually an increasing derivative. Also, you could tell by the shape of this graph that this is a concave upward. Can you see how it's cupped? It's curving towards up. So we're going to say that f double prime of x must be greater than 0 on this interval. Okay. What we call an inflection point. An inflection point is a point on a graph where the concavity switches from positive to negative or negative to positive. There are two ways to define an inflection point, and students must know them both. A function has an inflection point at c comma f of c if f prime changes from increasing to decreasing or decreasing to increasing, or if f double prime changes from positive to negative or negative to positive. So we don't have to distinguish whether we go positive to negative versus negative to positive. We just need to show that they change, that f double prime changes signs. Likewise, if we have the derivative of f, we just need to show that it changes from increasing to decreasing or decreasing to increasing. Let's take a look at this one. Consider the graph of f prime. All right, so this is f prime. We need to be careful with that because we are now at a point where we can be shown a graph of f prime, or f double prime. We really need to be careful about which one. Okay, for what intervals is f increasing? F is increasing wherever f prime is positive. So from -3 to -2 and -1 to 4. Why? Because f prime of x is positive. For what intervals is f of x decreasing? Well, that must be just from -2 to -1. And our justification is that f prime of x is negative. At what x value does f of x have a relative minimum or maximum? Well, we're going to have a relative maximum at -2. And that's because f prime changes from positive to negative there. In other words, the graph goes from increasing to start decreasing. Likewise, we have, let's see here, and f has a relative minimum at x equals -1 because f prime changes from negative to positive there. For what intervals is f of x concave up? We have the graph of f prime, so we need to describe concavity not by the sign of f double prime, but on the behavior of f prime. So f is concave up on the intervals where f prime is increasing. So that looks to be approximately -1.5 to 1. And perhaps maybe 3.5 or 3.4 to 4, a little less than 3.5, because f prime is increasing. Now, they do a good job on the AP exam making these graphs have all these important points happen at easy to read numbers, but you can excuse me for not being perfect about that, right? F is concave down everywhere else from -3 to -1.5. And let's see here, 1 to 3.4. Why? Because f prime is decreasing. And that's just the absolute definition of concavity. Concavity means that f prime is increasing or decreasing. What are the x values where f of x has a point of inflection? Well, f of x is going to have a point of inflection where the concavity switches. But the way we're supposed to justify it is by either saying f double prime changes sign or f prime changes from increasing to decreasing or decreasing to increasing. So we'll just say that f has an inflection point at x equals -1.5 and x equals 1 and x equals 3.4 because f prime changes from increasing to decreasing or decreasing to increasing there. All right. Let's look at an equation this time. We're going to describe the intervals of concavity and identify any points of inflection of the function. All right, let's work an equation this time. We're going to describe the intervals of concavity and identify any points of inflection. So to find intervals of concavity, we're going to need the second derivative. So we'll start by taking the first derivative. So y prime of x is equal to the derivative of e to the u, remember, is e to the u times u prime. which in this case is just x plus 3. To get the second derivative, it's going to be the product rule. So the derivative of the first is e to the u prime. Well, I actually already have an x plus 3, so this just becomes x plus 3 squared. Then plus, we have to do the first, which again is e to the x squared over 2 plus 3x times derivative of the second, which is just a 1. So I can set this equal to 0 to find the inflection points, and I'll factor out an x squared over e to the x squared over 2 plus 3x, which will give me x plus 3 squared plus 1. Now we can set each one of these equal to 0. This becomes e to the x squared over 2 plus 3x equals 0. But there's no solutions there because e to no power is 0. And then I can set x plus 3 squared plus 1 equal to 0. But that's not going to work either because I have x plus 3 squared equals negative 1. And that's non-real. So there are no values that make y double prime equal to 0. So we just need to look at the number line for the entire thing. So if I plug in any number at all, say 0 in the y double prime, what I'll get is 1 times 9 plus 1. I get a positive number. So that means that y must be concave up the entire time. So y is concave up from negative infinity to infinity because y double prime of x is greater than 0. And there are no points of inflection. Now, the first derivative definitely does equal 0 at negative 3. So if we look at the graph, which I have here, you can see that this graph definitely switches from decreasing to increasing at negative 3, but it's concave up everywhere. All right, I have a practice problem for you to do. I want you to find the intervals of concavity and any inflection points for the following functions. I have y equals cosine of 2x. Let's just go ahead and do that from negative pi to pi. Kind of missing an interval there. Don't want you to describe it everywhere. All right, and if you want, you can go down to part B as well, down here, and do the same thing. All right, pause the video and give it a try. All right, let's see how we're doing here. So the derivative here would be y prime is equal to negative sine of 2x times the derivative of the inside, which is a 2. All right, let's take the second derivative. It's going to end up being a negative 4 cosine of 2x because I'll have another times 2, so I went ahead and multiplied it. Now let's solve where this equals 0. So I have 0 equals negative 4 times cosine of 2x. So 0 is equal to just cosine 2x. So when does cosine equal 0? Well, cosine is equal to 0 at, let's say, negative pi over 2. Also, negative 3 pi over 2. I don't know. Would that be in the interval? Yeah, it would. Also at pi over 2 and 3 pi over 2. So remember, when you are trying to solve and you've got this number in front of your angle x, you really need to multiply your bounds by that number. So I really have to go from negative 2 pi to positive 2 pi. So that gives me x equals negative pi over 4, negative 3 pi over 4, pi over 4, and 3 pi over 4. So there's 4 different points here for us to consider. So negative 3 pi over 4. We're going all the way back to negative pi. Then we have negative pi over 4. We have positive pi over 4. 3 pi over 4. All the way up to pi. All right, so let's see here. If we plug in like a number like 0 into this value here, cosine of 0 is 1, so that's going to be negative. And usually with trig, these just kind of alternate like that. So in this region here, remember we're going to be timesing these angles by 2. well, then we would definitely be in quadrant 2 because we're doubling this angle. And that's where cosine is negative, and a negative times a negative is a positive. Then over here, if I double an angle down here in this quadrant here, this is going to end up in the 4th quadrant when I'm done. So it'll be positive again, which makes it negative. This will be positive. This will be negative. So we can say that y is concave down on these intervals from negative pi to negative 3 pi over 4, negative pi over 4 to pi over 4, and 3 pi over 4 to pi, because y double prime is less than 0. It's concave up on negative 3 pi over 4 to negative pi over 4, and pi over 4 to 3 pi over 4, because y double prime is positive there. And we have inflection points at, let's see here, negative 3 pi over 4. Let's go ahead and plug that in. That would be the cosine of negative 3 pi over 2, which is 0. And then we have negative pi over 4. So that'd be a negative pi over 2, which is also 0. Then we have pi over 4. And I'm getting a pattern here. That would become pi over 2, which is 0. And this last one will be 0 as well at 3 pi over 4, comma 0. And I'm running out of room, but the reason is because y double prime changes sign. Okay, let's take a look at the next one. Let's get the first derivative. F prime of x is equal to, we're going to do the derivative of the first, which is 1, times the second, and I'll use exponent notation here. Plus the first times derivative of the second. Bring down the 1/2. 9 minus x squared to the negative 1/2, and then multiply by the chain, which is a negative 2x. Since I'm going to be taking the second derivative, I might as well go ahead and clean this up just a hair. We get, let's see here, 9 minus x squared to the 1/2 minus x squared times 9 minus x squared to the negative 1/2. And I'm actually going to factor out a 9 minus x squared to the negative 1/2, which will give me 9 minus x squared to the first minus x squared. So as you can see, f prime of x is actually 9 minus 2x squared over 9 minus x squared to the 1/2. Let's take the second derivative. So it'll be low d high minus high d low. So that's going to be a 1/2 9 minus x squared to the negative 1/2 times negative 2x. All over low, low, which is actually just 9 minus x squared now. And I am definitely going to need to have some more room here. So let me move this down, at least temporarily. Okay. All right, well, what can we do with all this? Let's see here. I'm hoping that some nice little magic happens that makes this a lot better, a lot fast, real fast. All right, well, this is going to cancel that, and that minus will cancel that. So I see 9 minus x squared to the 1/2 times a negative 4x plus 9 minus 2x squared times 9 minus x squared to the negative 1/2 times x, all over 9 minus x squared. And what I'm going to do is I'm going to factor out the smaller of the two powers of 9 minus x squared, which is actually a negative 1/2. And when I do that, I'll move it to the bottom and it'll join with this. So that's 2 halves plus 1 half is 3 halves. So we're going to have 9 minus x squared to the 3 halves on bottom. And this will be a negative 4x. And remember, we're dividing this by 9 minus x squared to the negative 1 half. So it's going to become 9 minus x squared to the first plus. We have 9x. When I distribute that, that's going to be a 1. So 9x minus 2x cubed. All right, so this numerator finally becomes a negative 36x plus 4x cubed plus 9x minus 2x cubed, which is, let's see here, 2x cubed. Minus 27x all over 9 minus x squared to the 3 halves. We'll factor out an x, and I get 2x squared minus 27 over 9 minus x squared to the 3 halves. All right, we are now finally ready to make our number line. So we can see that this numerator is going to equal 0 at 0. And then also at a value like, if you solve that, the square root of 27 over 2 and negative 27 over 2. But we also need to consider this square root here. We've got 9 minus x squared inside of a square root. This function is only defined from negative 3 to 3. Which, the square root of 27 over 2 is actually outside of that. The 27 over 2 is what? 13 and a half. So the square root of 13 and a half is, clearly more than 3. Something a little more than 3 because the square root of 9 is 3. So we actually can't use those values to, they're not in the function's domain, so it doesn't matter that they would equal 0 in the numerator. If we plug in a number like 1, we'll get a negative number here. And let's see here, this is going to always be positive. So a negative there. Now, if I plug in a negative number here, like a negative 1, I would get a negative 1 times a negative number, so that's going to be a positive here. So what we can see is that this function is concave up on negative 3 to 0. It's concave down on 0 to 3. So let's take a look at that right quick. And I've got, there's the original and there's the second derivative, you can see. So here's where it's concave up, and then here's where it switches to concave down. All right, I'm going to erase all that because I don't need that anymore. Oops. So that was a tough one. Probably won't get algebra that intense. Maybe one question, but it would be probably on a multiple choice. I just, they probably would have given you the first derivative as well. I just don't expect you to have to worry about the algebra being that bad, but it's good for us to go through it anyway. All right, practice 4.2. Describe the intervals of increasing, decreasing f of x and the intervals of concavity. Give it a try. Okay, to get intervals of increasing and decreasing, that's the first derivative. So I'll take f prime of x is equal to low d high minus high d low all over low low. So this cleans up as just a negative 2 over x minus 2 squared. Well, this is actually negative everywhere, right? Because this bottom is never positive because it's squared. So this is negative everywhere except for at x equals 2 because f is not defined at 2. So we could maybe make a note about that. Discontinuity at x equals 2. So I'm going to go ahead and say that f is decreasing on the interval from negative infinity to 2, union 2 to infinity. And the reason why is because f prime of x is negative there. Let's take the second derivative. So I'm going to rewrite this as negative 2 times x minus 2 to the negative 2 power. And then the second derivative would become 4 times x minus 2 to the negative third, which is 4 over x minus 2. Well, the second derivative is always positive. So we're going to say f is concave up. Oh, wait, it's not always positive. I'm sorry. This is because this numerator is not always, this denominator is not always negative. Let's do a little number line. So f double prime, we got, let's see here. We know we're undefined at 2, right? So if I plug in a number like 0, I'll get 4 over a negative number. If I plug in a number like 3, I get 4 over a positive number. So we're concave up on 2 to infinity because f double prime is greater than 0. And we are concave down on negative infinity at 2 because f double prime is less than 0. And I think a graph would be interesting to look at for sure. So let's take a look. We said we were decreasing everywhere, and it is. From left to right, we're decreasing everywhere. This is concave down, but this is concave up, which is what we said. All right, let's take a look at our next problem. All right, given that f of x equals x to the fourth minus 4x cubed, find the intervals of increasing and decreasing, the intervals of concavity, the relative extremity, the points of inflection, and sketch the graph. All right, well, we'll try it. So f prime of x, f is continuous everywhere, by the way, just take note of that, 4x cubed minus 12x squared. Let's find f double prime while we're at it. That would be 12x squared minus 24x. All right, so when does f prime equal 0? Well, let's set it equal to 0, and I'm going to factor out a 4x squared, and I'll be left with an x minus 3, I believe. So I get x equals 0 and x equals 3. Let's draw a number line. So 0 and 3. So if I plug in like a 1, I would get a positive times a negative. That's a negative. A negative 1, like a negative 1, I'd get a, well, it's positive still because it's squared, and then still times negative, so negative. Then if I plug in a number bigger than 3, it'll be positive. So we could see that f is increasing on 3 to infinity because f prime is greater than 0. F is decreasing on negative infinity to 0 and 0 to 3 because f prime is less than 0. All right, let's take a look at the second derivative. Let's find out what my intervals of concavity are. If I factor out an x, a 12x there, I can get that f double prime is equal to 0, and factor out 12x, I get x minus 2. We can see it equals 0 at 0 and 2, right? But this one's going to go plus minus plus. So f is concave up from negative infinity to 0 and from 2 to infinity. F is concave down on 0 to 2. What's my justification? Because f double prime is less than 0, and this one is f double prime is greater than 0. And since I've already taken the second derivative, I could use the first derivative test here easily, or the second derivative test. We'll use the second derivative just for fun. So f double prime exists everywhere. We just need it to exist on an open interval around our critical numbers. And I'm going to say that f double prime of 3 is greater than 0. So 3 comma, let's see, that's 3 to the fourth. 3 to the fourth is 81. And then 4 times the 27 is negative 108. So let's see, 108 minus, what did I say, 81? All right, so a negative 27. All right. That right there is a relative min. Let's see here. X equals 0 is not a relative minimum because we could see that from the first derivative it didn't switch signs. Let me say by the second derivative test. We could have just as easily used the first derivative and shown that since f prime changed from negative to positive there. Notice the second derivative test fails at x equals 0 because it's 0. If the second derivative is 0, then the second derivative test fails. All right, we know that f has an inflection point. It has a couple of them, right? It has inflection points at 0, 0, and 2, hopefully the math is here. 2 to the 4th is 16. 16 minus 32, right? 2 to the 8th, 16 minus 32, that's a negative 16, right? Because f double prime changes sign there. All right, we were asked to sketch it with all this information, so let's give it a try. So 1, 2, 3, and 4. I want to say the x-intercepts, if I noticed where it looked like there were x equals 0 and x equals 4, and I think they are. So at 3, negative 27. So let's see here. Let's count by 5s. 5, 10, 15, 20, 25, 30. So 3, negative 27 would be right there. That's our minimum. 2, negative 16, that'd be about right here. That's a point of inflection. And 0, 0 is also a point of inflection. So we're going to be coming down. We're going to be concave up. We're going to switch to concave down. And we're going to switch to concave up. We'll be concave up the rest of the way and start increasing. So it begs the question, how good a job did our calculus do at telling us how to graph this thing? That would be worthwhile to know, right? So let's find out. X to the 4th, was it minus 4x cubed? And let me see here. I'm going to set my settings. We counted by, let me hide it real quick. I don't want to see it. So we went from about like maybe negative 2 to 5. We'll say that. And we went from about 10 to negative 30. We went by 5s. We went by 1s. Okay. Well, something's not right here. Oh, I didn't do it right. Negative 30 to, put the wrong number first, to 5. Let's try that. All right, show me. Okay, there's our inflection point. There should be another one here somewhere. There's another inflection point. There's our minimum. Pretty cool, huh? Did we do a pretty good job? I think we did. All right, speaking of which, let's see how good we can graph given this information. Sketch the graph of a continuous function with f with given the characteristics. F of 0 is equal to f of 2, which is equal to 0. Okay, we can do that. So let me just say 1, 2, 3. So f of 0 equals 0. F of 2 is equal to 0. F prime of x is greater than 0 if x is less than 1. Okay, so that means that we are increasing from 0 to 1. Or we're increasing over here. We're definitely increasing. What about the concavity, though? Well, it says that we're concave down all the time. Okay, so we're concave down all the time. We're going to increase up until we get to x equals 1, where we're going to be flat. Then it says that the first derivative is negative if we're bigger than 1. So we must come down here like so. Okay. See if you can't do one. Oh, no, we got one more practice problem together. Let's see here. We're going from 1 to 2 again. This time we're positive. We're increasing again. Then we'll be decreasing. But f of 1 is f prime 1 is undefined, and we're always concave up. Okay, so this is still going to be a maximum, but this time we're going to be like this, and we're going to hit a cusp. So it's going to have to be like that. So we're always concave up. All right. Now you try one. Sketch a possible graph here. All right, let's see what you did. 1, 2, 3, 4, 5, and 6. So those are my zeros there and there. F prime of 3 is equal to F prime of 5, which is equal to a 0. So we're going to have a horizontal tangent line. We're going to be increasing to 3. Then we're going to be increasing again to 5. So we're going to be going something like this and then level out again. Then we're going to decrease after 5. We're going to be concave down up to 3. So which is kind of what we expected. So up to 3, we're going to be concave down. Then we're going to hit like a horizontal tangent line, switch to concave up till about 4. Then from then on, we're going to be concave down till we hit 5. And then we're still going to be concave down, but we're going to hit a maximum at 5. So kind of like that. All right. So I think that's it for this lesson. So that's all about concavity and second derivative. All right. Take care.